very good day. My name is NURUL NABILA binti Wakiman. My topic for this research is silver catalyzed free radical alkylation of NAPTHOQUINONE. For the introduction, I will explain about compound NAPTHOQUINONE and menadione. Firstly, NAPTHOQUINONE is a naturally occurring compound derived from naphthalene. When two benzene ring atoms in the naphthalene nucleus undergo oxidation, it results in 1,4-naphthoquinone. So the quinone ring contains double bond conjugated with carbonyl groups, making it reactive to reduction, oxidation, and nucleophilic attacks from oxygen, nitrogen, and sulfur nucleophiles. Agents can rapidly reduce 1,4-naphthoquinone to form 1,4-dihydroxynaphthalene. This is the second compound shown in this slide is menadione, or can be called as 2-methyl-1,4-naphthoquinone. Menadione is a synthetic naphthoquinone derivative that is crucial for synthesizing vitamin K1 and K2. Manufacturing menadione rather than naturally occurring, it plays a vital role in animal physiology, regulating blood clotting, and bone calcification. Intestinal microbiota can convert menadione to vitamin K2 in the intestine, and alkylation in the liver leads to its conversion in humans. Menadione's role extends beyond being a precursor to vitamin K1 and K2. It also exhibits diverse effects, including anti-cancer, antibacterial, antifungal. The interactions between nucleophilic biomolecules and the 1,4-quinonic nucleus of menadione results in its redox cycle. In this slide, shows the naphthoquinone derivatives such as juglone, planbenene, lausol, and for the other side are the menadione derivatives such as vitamin K1, vitamin K2, and menadione. Next, I will explain about the problem statement in this research. The problem statement are a large amount of chemicals is needed in the synthesis of menadione. The manufacturing of naphthoquinones is time-demanding and requires numerous phases of synthesis. The isolation process of natural product yields small amount of products. And as for the research questions in this research, are how to introduce the synthesis time by listening or combining the steps for synthesis process, how to create a low-cost synthesis process by using cheaper and lower amount of chemicals, and is there any possible pathway in the synthesis process that can produce high-yield products. As for the objectives in this research is to purify and isolate natural naphthoquinone from the synthesis process, to develop a more cost-effective methyl naphthoquinone production method, to characterize and identify the compounds with spectrochemistry techniques. Significance of study are discovery methods for improving synthesis process of methyl naphthoquinone that show effectiveness and produce large number of products, discovery methods of synthesis of methyl naphthoquinone in low-cost pathway and using less chemicals in the process, discovery biological properties of naphthoquinone's medicinal application either in traditional or modern way, and discovering alternative pathway to produce higher quality of naphthoquinone at lower cost. So in this research, for the expected output or outcomes or implication are the production of new naphthoquinone derivatives that suitable for medicinal and pharmaceutical chemistry, the identification of the need for producing naphthoquinone derivatives at a cheap cost in a short period of time and with few components. Lastly is the ability to produce naphthoquinone derivatives with expected or short. Next session is literature review. In this session, I will explain about the study I have done in some research paper. The first one is the research about alkylation or dialkylation of 1,4-naphthoquinone. The reaction occurs from naphthoquinone compound that underwent reaction A, as shown in the slide, which is radical Hanniske oxidative decarboxylation or oxymethyl addition in the presence of ethanoic acid, NH4-2S2O8, silver nitrate, CH3CN, and water at temperature 80 degrees Celsius for 7 hours. And the product become as alkyl naphthoquinone with 95% yields. Then, for reaction B, the alkyl naphthoquinone underwent wet sulfur type epoxidation or epoxide cleavage and underwent the same condition as reaction A with presence of CH3, CH2, 9COOH, and H4-2S2O8, silver nitrate, CH3CN with water at temperature within at 60 to 70 degrees Celsius for 7 hours, and obtained dialkylated naphthoquinone compound with 53% of yields. Next is the research about alkylation of bromo-naphthoquinone compound. Firstly, for the reaction A, the bromo-naphthoquinone underwent radical Hanniske oxidative decarboxylation or oxymethyl addition in the presence of ethanoic acid, NH4-2S2O8, silver nitrate, CH3CN, and water at within 60 to 70 degrees Celsius for about 7 hours. The product is bromo-naphthoquinone compound. Then, the bromo-naphthoquinone underwent nucleophilic substitution in the presence of KOH or MEOH in the condition of reflux at temperature around 60 to 70 degrees Celsius for 1 hour. The product obtained is hydroxyquinone with 51% yields. Further study is about alkylation of hydroxy-1,4-naphthoquinone. The compound underwent condensation process with aldehyde in acidic conditions. The reagents that were used were glacial acetic acid, hydrochloric acid, aldehyde, ether, aldehyde, either propanal, butanal, or hexanal, that was heated at 60 degrees Celsius. Then mixed with water and kept in the dark for overnight. The product obtained was hydroxynaphthoquinone that appeared as solid crystal of orange in color. And last but not least is the research about alkylation process of 2-methyl-1,4-naphthoquinone to produce fluoroalkylated naphthoquinone compound. First reaction was the direct perfluoroalkylation of 2-methyl-1,4-naphthoquinone with PFTA peroxides in the presence of CH2Cl2 with the conditions of reflux at 40 degrees Celsius for 8 hours and produced fluoroalkylated naphthoquinone compound, which was 2-methyl-3-perfluoroethyl-1,4-naphthoquinone with 74% yields. Secondly was the same reaction and condition as the first one, by it being done in the presence of one hexene that produced 2-methyl-3-1,2,2,3,3 prime pentafluoropropylpentyl 1,4-naphthoquinone with 90% yields. Next section that I want to explain is methodology that I have been done in my research topic. In this research, I have done two reactions with the starting material menadione. First reaction was menadione with hexanoic acid that produced the product compound 47. Second reaction was menadione with lauric acid that produced compound 48. So for the steps that have been done in the reactions was firstly, the starting material, which is menadione and hexanoic acid or lauric acid, were dissolved in acetonitrile. Then a mixture of silver nitrate in distilled water was added to the solution. The temperature was then raised to 75 Celsius and a solution of potassium persulfate in distilled water was slowly drippled into the mixture over several minutes. The reaction progress was then monitored hourly using TLC until completion. Afterward, dichloromethane was added to the reaction mixture, which was then cooled, and the organic layer was extracted using a separatory funnel. The organic layer was washed 3 times with distilled water, dried with anhydrous sodium sulfate, and filtered. Excess solvent was removed using a rotary evaporator, resulting in a crude product. This crude product was then purified using short column chromatography with a solvent system of hexane ethyl acetate with the ratio 9:1. The final yellow solid product was further dried under high vacuum for 8 hours. Result and discussion. Synthesis of compound 47. The reaction of menadione plus hexanoic acid resulted compound 47. The spectrum in this slide show the successful synthesis of the target compound, and a proposed radical mechanism explain the key steps involved in the reaction. On the IR spectrum, as shown in the table, indicated characteristic absorption bands for aromatic CH band, C double bond C stretch in aromatic compounds, C double bond C stretch in alkenes, and the C double bond O carbonyl group. As for the proton NMR data, it revealed peaks corresponding to the aromatic protons, which is CH2 adjacent to the aromatic ring, CH2 adjacent to the aromatic ring, and also RCH2 3R and RCH3 group. The carbon-13 NMR spectrum for compound 47 identified peaks for the C double bond O group, CCH3 adjacent to the alkene, CCH2 adjacent to the quinone moiety, and also C double bond C aromatic region, and there also the alkene chain in the peaks. Synthesis of compound 48. The reaction between menadione and lauric acid resulted compound 48. So the successful synthesis of the target compound is shown by various spectroscopic techniques, and it proposed radical mechanism that explain the key steps involved in the reaction. In this slide, it shows the IR spectrum interpretation that reveal characteristic absorption bands indicating CH band aromatic, C double bond C stretch in aromatic compounds, C double bond C stretch in alkenes, and also the C double bond O of carbonyl group. As for the proton NMR data for compound 48, it indicated peaks for aromatic protons, methyl hydrogens adjacent to the aromatic ring, hydrogen in the methylene group adjacent to the aromatic ring, and hydrogen in the carbon-13 NMR spectrum for compound 48 identify resonance peaks for the C double bond O quinone group, CCH3 adjacent to the aromatic compound, CR group within the alkene structure, C double bond C within the aromatic ring, and also the methylene carbons in the alkene group. In conclusion, reaction of menadione with hexanoic acid resulted compound 47 with 99.93% of yields, and subsequently reaction of menadione with lauric acid resulted compound 48 with 35.72% of yields. All the structures were confirmed with spectroscopy analysis, which are proton NMR, carbon-13 NMR, and IR spectra. To increase the product yield, it is recommended to increase the temperature and increase the concentration of potassium persulfate. And also, it is recommended to try alternative catalyst modifications such as organocatalysts like proline. My presentation about the silver catalyzed free radical alkylation of naphthoquinones has come to an end. That's all from